Okay, so let's look at the idea of projecting our acceleration vector on our unit tangent vector. Now here I've sketched the velocity vector, which might be longer or shorter, and our unit tangent vector in the direction of motion. To project, we simply project over here at a right angle to the line of our unit tangent vector, and we get our parallel component of A. So I can say this. We've already done the projection of V on A, okay? That's got to be equal to the projection on T of A because V and T have the same line, and all we're doing to project A onto a vector is projecting onto the line of that vector. So V and T have the same line, so both of these projections are the same. And the projection of A on T we would write as A dot T over magnitude of T multiplied by T over magnitude of T. Okay? This being this side of the triangle, the length of this side of the triangle, negative if this happens to be in the direction opposite T. Length of this side multiplied by the unit vector in this direction gives us the projection vector from here to here. Okay? Now, so that's side of the triangle times unit vector. Now, T's already a unit vector. That simplifies things a lot because the magnitude of T is 1, both here and here, so we don't even have to write it. It's just A dot T multiplied by T. There's our projection. And that is our parallel component of A. And I don't think I ever actually wrote that down. So, the reason this is important is that's what we call the parallel component of A. The component of A in your direction of motion, the component of your acceleration that speeds you up or slows you down, pushes you from behind, or causes you to, tend to go forward. That's this one. The perpendicular component is the one that changes your direction. That's what you feel when you go around a curve. You feel like you're being spun to the outside. Well, that's because you're being pushed to the inside, but your inertia doesn't want to be pushed to the inside. So you got to exert some force to keep going to the inside. Okay. So having found A parallel, we can easily find A perpendicular by subtracting, getting the normal vector A perpendicular over the magnitude of A perpendicular. Okay, and we've already done this, so we just take this divided by the magnitude. This vector is normal to the curve. It's an inward normal. So when we divide by its magnitude, it's a unit inward normal, and that's what we're calling capital N. There's another way to calculate capital N that I thought that I indicated it over here. Okay, you could do this if you wanted to. Okay, now this is what I was talking about earlier when I talked about really messy calculations. Okay, first of all, V of T, pretty easy to take the derivative of V of T for the kind of function we've been looking at, and get your A of T. Okay. If I want to do the derivative of the unit tangent vector, though, it's got your V of T, but it's got this thing down here, which is a big old square root with a bunch of squares in it. It might be messy already, but you're going to have to use a quotient rule. If you didn't have to already, you will now. And if you did before, it's even worse. So you divide V by its magnitude to get T, and then you try to take the derivative of T to get your normal vector. That's messy, typically. We can contrive examples where it isn't, but usually it really is. And then we got to divide that by its magnitude, which just adds insult to injury. And you have pages. Well, it's good for your experience and good for your practice in taking derivatives to do that once in a while. But this is really the easier way to find it. So our picture is this. Here's our unit tangent vector. Here's our acceleration vector. Here's our unit normal vector. You do A dot T and multiply it by T, and you get your acceleration vector in your direction of motion. and then you do A dot n and multiply that by n, and you get your centripetal force, or your centripetal acceleration, the acceleration that keeps pushing you toward the middle and changes your direction. So there it is. And your centripetal acceleration is your perpendicular component of your acceleration. Now, if you're moving around a circle, it's easy to derive. You just start with this picture and do a little stuff. And we'll probably do that. If we don't do it here, we'll do it in physics, and I think everybody in this course is in my physics course. The perpendicular component of A is just v squared over r. Hence magnitude v squared over r. So I don't have arrows over this, so I'm just talking about magnitude. There's no arrow over v, so I'm just talking about the magnitude of v. And that is the formula I think a lot of you know for centripetal acceleration. Might not have derived it, but if you haven't, you know, very likely that we will. Okay, so it's a very neat picture. Now there's even a little more to the picture. You've got your unit tangent and unit normal vector. So you're moving along this curve, okay? So you're here, and you're moving kind of in this plane right here. Here's your unit tangent vector, or your direction vector, and here's your normal vector. Well, if you take the cross product of those two vectors, you've got a coordinate system. You've got this vector, you've got this vector, and you've got this vector. So you've got a three-dimensional coordinate system following you along. You already know how to calculate the component of your acceleration in the direction of this vector and in the direction of this vector. What's this vector tell you? Well, as you move along, these vectors change, and the direction of this vector is normal to the plane in which you are temporarily moving. So if you want to know in what plane you're moving at a given instant, figure out your position at that instant, figure out this vector and this vector, your unit tangent, unit normal vectors, take their cross product, there's your normal vector, and it becomes really easy to find your plane. And that's often something you really want to do. It's also a really important thing to be able to visualize. So, all I'm saying here is we call this vector B, the t cross n vector. We call it your binormal vector. Your binormal vector is a unit vector because the cross product of two perpendicular unit vectors is a unit vector. Think about that. And it's got to be perpendicular, both t and n. So you have this right angle coordinate system. Everything at a right angle. This forms a moving rectangular coordinate system. So, one question that you might want to ponder, I'm not going to address it right now, what's the meaning of dB dt? What's it feel like? You're out flying your one of your spare fighter jets, and you know you're doing all kinds of things. What's your experience of that binormal? What's your experience of unit tangent, unit normal vector, and the acceleration components? So it gets kind of hairy to really be able to think and see this clearly. Some people are better at visualizing than others, but we'll at least be able to do calculations. We'll at least have some idea of what the calculations mean. Okay, the better you can visualize, the better you understand what they mean, but you still have a sense of what they're meaning, even if you aren't great at visualizing, as most people aren't. Okay, so that's a pretty neat picture. And once we get that wrapped up, we can start into all kinds of neat stuff. I mean, this is neat to start with, so plenty of stuff to look at here.